First, we talk about the fundamental concepts of atomic structure. And we know that the atoms, they are the basic building blocks of the matters in the universe. And we know that for each atom, we have electrons. Electrons, and this is the mass is 9.11 e power negative 31 the kilogram. So it's very, very small. This number is very, very small. In addition to electrons, we have protons and neutrons for each of these atoms. And protons and neutrons, and their mass are 1.67 e negative 27 kilogram. So this is the atom. Each atom usually contains electrons, protons, and neutrons. And then we talk about atomic number Z. This Z is the number of protons in nucleus of atom. The nucleus, we know that this is a nucleus. Nucleus contains protons and neutrons. And also it equals the number of electrons for electrically neutral matter. So this is a neutron. We will not talk about neutron here. So this is atomic number equals the number of protons and also equals the number of electrons for electrically neutral atom. Why this is electrically neutral atom? Because if it is ion, that is another story. Because some electrons will be transferred from one atom to another atom. And so here you should know that atomic number Z, it includes the number of protons and also the number of electrons for electrically neutral atom. And the third point I want to talk is the atomic number ranges in integral units, and we always see the integral units from 1 to hydrogen. 1 for hydrogen. Hydrogen is latest element, hydrogen, and to 92 for uranium. And uranium is the raw material, and to build this is atomic bombs. And so this is uranium is the highest. 92 is the highest of the naturally occurring elements. You pay attention to this. This is a phrase, naturally occurring elements. Well, there is some man-made elements, and they have higher atomic number than this 92. And you can, if you are interested, and you can just look, search in the literature to see what kind of man-made elements, and they have higher atomic numbers than uranium. And then we talk about fundamental concepts of atomic structures. Atomic mass A of a specific atom, and is expressed as the sum of the mass of the proton and the neutrons within the nucleus. Because electrons usually is very, very light. Electrons are very, very light, and we only include these protons and neutrons when we compute atomic mass A. And then I introduce important concept, isotope. As the name suggests, the isotope means that whenever you see icer, it means something is the same. Isotope here means that any of two or more forms of chemical element and having the same number of protons in a nucleus, or the same atomic number, but having different numbers of neutrons in the nucleus, or the different atomic masses, because the neutrons and protons, they determine atomic mass. The proton itself determines the atomic number. You should know that. Isotope, this is isotope. This is a common isotope. We have hydrogen, deuterium, and tritium. So both of these three elements, and they have the same number of protons, but they have different number of atomic mass. So these three guys, hydrogen, deuterium, and tritium, and they are called isotope of hydrogen. So I'll just give you one example. So you can, if you are interested, and you can just look into the literature to see other commonly known isotopes. Then we talk about atomic weight. So this concept corresponds to the weighted average of atomic masses of atoms naturally occurring isotopes. For example, for hydrogen, we have three different elements. We have hydrogen, deuterium, and tritium. And in order to calculate atomic weight, we need to take the average value of hydrogen, deuterium, and tritium. And so I will show you how to calculate this atomic weight in the following slides, in the following lectures. And then we talk about other fundamental concepts. So these concepts, atomic mass unit, and we denote this one for short as AMU, and it equals 1/12, 1/12 atomic mass of carbon 12, and can be used to compute atomic weight. So why we use carbon 12? And the carbon 12 is the most important element in the universe. It indicates if it is possible, impossible that in this environment we have any biological atoms here. So this is for this reason, this carbon 12 is treated as the most important element in the universe, at least for the universe we are living. And then we talk about atomic weight. Atomic weight is weight of 6.022 E23 molecules or atoms. So this is a very, very huge number. So this is a very, very huge number, atomic weight of so many molecules, because molecules and atoms, each of these molecules and atoms, and their weight is very, very small. So we need to, in order to, for the convenience of calculation or doing research or the practical purposes, and we multiply. So this is atomic, the weight of the molecule or the atom by a huge number. And so this is the 1 AMU over 1 ATOM atom, we call 1 G/mole. And so this is the mole is the number, MOLU is a number. So this is a number 6.022 multiplied by E23. So this huge number. So you need to know that. C atomic weight equals, for the carbon, equals 12.011. For hydrogen, it equals 1.008. And for other atoms, we can calculate other atom the weight using this equation, using this the formula. So you can see hydrogen is the lightest element in the universe, at least in the universe that we are living. And then we talk about the schematic representation of the Bohr atom. So there are several models to describe the behavior of atom. The Bohr, it is genius, the scientist, and he proposed a model. So this is a Bohr's model. You can see that. And so we have this nucleus, and we have here, this is orbital of electrons. So this nucleus, so we have several orbital orbits for neutrons. For electrons. So this is electrons are assumed to revolving around the atomic nucleus in discrete, this is orbitals in discrete orbitals, and you can see that these orbitals, they are not continuous, and the position of any particular electron is more or less defined in its orbital. So energy states, then we talk about energy states of Bohr, the hydrogen atom. So this just to give you one example here. And so here is, this is energy level. This is energy level. And so here we can have different energy states. And you can see the first three electrons, energy states, and for the Bohr hydrogen atoms. So here A, for 1, 2, 3, so energy level here. So here is for the B, electron energy states, and for the first three shells of the wave mechanical hydrogen atom. So wave mechanical hydrogen atom. So 1s, so this is sp and spd, and we know that, right? So if you have taken this is a chemistry courses in high school, and you will have some basic understanding of these different orbitals, and we call different layers. And you can see S1, this is number 1 layer. For each layer, we have several sublayers. So this is S, P, and D. So this is a wave mechanical atom model. This is another model. So this is the here is a comparison of Bohr and wave mechanical atom models. So this is the probability. This is the probability from 0 to 1. For this is a nucleus. This is a nucleus, and for here, these orbital electrons. And so here is this probability. The comparison of the A is this is a Bohr's model, and B is wave mechanical atom model, and in terms of electron distribution, and in terms of electron distribution, you can see here is a cloud here, and for this is wave mechanical atom model. But for this Bohr's model, and we only have this is one single orbital here, and you can see very clearly the distance. So here is a probability here. This is a probability, and so you can see the Bohr and the wave mechanical atom models, and they are proposed by different people. I will not say which one is right, which one is wrong. Both of them are right. And it is one thing is that how they are close to the reality, and both of them, and they have revealed some truths, but to better understand this structure of atom or atom models, and we might combine both these series, both these models, Bohr's model and wave mechanical model. And then we talk about electronic structure. Electrons, they have wave-like art and these particulate their properties. And so whether wave-like and particulate these properties, and Albert Einstein revealed the truth that electrons have a wave-like and particulate the properties. So this means that the electrons are in orbitals defined by a probability, and each orbital at a discrete energy level is determined by quantum numbers. For example, here is a quantum number. This is a quantum number, and here is a designation. The quantum number n, and this is a principal and energy level shell, and L is subshell orbitals, and subshell orbitals here. So ML is the number of energy states for each subshell. MS stands for the spin. For here, designation we have for the N, we have KLMNO, we have 1, 2, 3, and etc. So subshell we have SPDF and SPDF, and for ML we have 1, 3, 5, 7, from minus L and to this positive L, and the spin is 1/2 and minus 1/2. So this is how we denote this electronic structure. And here is one example here. Electrons have discrete energy states, and electrons tend to occupy lowest available energy state. So this is understandable because we have learned that for each system, the system has a tendency to remain lowest energy level, because lowest energy level is the most stable state. For here is energy, okay, so energy 1s here, 1s, 2, s2p, 3s, 3p, 4s. We have this 3D here. Sometimes the energy level of 3D is a little bit higher than 4s. That's the reason 4s is a little bit lower than 3D graphically. So we have 4p, 4D here. And so for here, we K is shell 1, number 1, L shell number 2, M shell number 3, and this N shell number 4. And so here is the lowest level, and here is a higher level. And then we take a look at the survey of elements. The most elements, the electron configuration, and is not stable. It's not stable. Okay? So you can see here elements hydrogen, helium, and for hydrogen they have atomic number 1, helium atomic number 2, electron configuration 1s1 and 1s2, and helium is stable. Why? Because this 2 is the maximum number the layer S can have. So that's the reason. So this helium is stable. It means that this guy does not have the tendency to either give electrons to other atoms or obtain electrons from atoms to achieve a stable state. That means helium is chemically stable. And then we look at the second section: lithium, beryllium, boron, carbon, and finally we reach this neutron. We can see the neutron here. Okay, so neutron is 1s2, 2s2, 2p6. For the second layer, 2. For second layer, we have s2 and p6 totally, and this guy has 8 electrons in the shell, second shell. So that means this guy also, the number of electrons in neutron is also reaching the maximum number, and so of maximum number for this shell. And this is the reason that neutron does not have tendency to have chemical reaction with other atoms in order to maintain a stable state. It's the same thing as we talked about this helium. So that's the reason this neutron is also stable. And if we go further down, sodium, magnesium, aluminum, finally we reach this argon here. This argon, we can see the argon for the third shell, 3s2, 3p6, and 2 plus 6 equals 8. Also, and so this 8 is the biggest number of electrons, in the outer layer. So as a result, for argon, the electrons reaches the biggest number. So argon is stable. It does not have tendency to have chemical reaction with other atoms. And then we also want to say krypton. Krypton is also for the 4s here, S2 and P6. So this guy is also stable because the same reason as we talk about helium, neutron, and argon. Helium, neutron, argon, along with krypton, and they are called inert elements because they do not have tendency to have chemical reactions with other atoms in order to reach the stable state because themselves they already they are in the same in the stable the state. I need to let you know, guys. So here, valence, and so this is a very, very important concept, valence. Valence, when we talk about valence, it means that we talk about the outer layer, outer shell. Outer shell usually not filled completely. If this is the case, so this guy has a tendency to have chemical reaction with outside or with other atoms. This means that this guy is not stable. On the contrary, helium, neutron, argon, and krypton, these four guys listed here, and they are chemically stable. And so that's the reason they are called inert elements. Any questions? Okay, if there's no question, we move on to next slide. Electron configurations. Valence electrons, you need to know that valence electrons, those in the unfilled shells usually is under this outest shell, and filled shells more stable. And valence electrons are most available for bonding and tend to control the chemical properties. Right? For example, this is the carbon and for which the atomic number equals 6. So this guy have 2s2 and 2p2. And so 1s2 here. This is the first shell and this is the second shell. This is the second shell and this guy only has 2 plus 2, 4 electrons, which is not stable. And for stable, we need to have 8 electrons in the second shell. So this is called valence electrons. And give you another example of this is iron. So the iron is atomic number, right? This is atomic number and equals 26. And so here you see this is energy level of different shells. And K shell, L shell, M shell, along with N shell. And we have 1s, 2s, 2p, 3s, 3p. This is 3d here. So this is 4s, the energy level for 4s is a little bit lower than the 3d. That's the reason graphically and 4s, this we list 4s below this 3d. So we have this positive and negative 1/2 and minus 1/2. These are spins there. The same thing for other states. So this is for three here. Okay, we have valence electrons. Valence electrons and 3d and 4s. This is called valence electrons. And then we talk about the periodic table. Periodic table. This is periodic table, and maybe if you have taken the chemistry in high school, you know some information about this periodic table. Periodic table here, you can see, so column, for each column, and they have the similar valence structures. As a result, for each column, they have the similar chemical properties. And so here is, so we have these two arrows. So this arrow, electropositive elements. So here is electronegative elements. So rapidly acquire electrons to become ions. So here, rapidly give up electrons to become positive ions. So we can see we have, so here is for this one, so we have, they can give up one electrons to achieve a stable state. And for here, this is inert, the gases, and I told you guys already. So this is helium, neutron, argon, krypton. This is Xe and Rn, and so this column they are called inert elements. For here, so this is F. So this is FCl, Br. This is IAT. So they can acquire one electrons and to become this is to reach the steady state. For this one, they need to accept two ions. And so this color is metal, and so this dark color is a non-metal. And so this is for this one, these are two different triangles of color, different colors, and we call intermediate. So electronegativity value is rigid from 0.7 to this is 4.0, and 0.7 is F here. F is, we know that F is the most active element in the world, and this guy can have can almost have chemical reactions with any of other atoms. So that's the reason this guy is most dangerous element. This is FR here, and it has 0.7, and so it has this one. So this one is very chemical reactive, chemical active also. So this is a smaller electron negativity. So this is a larger electron negativity. So these two extreme elements, they are very chemically active. So be very careful. If you are handling these two elements, be very careful. And this the experience, the story is some. This is we call the stories. We call this and the facts. The facts show that, and whenever people use the F, and they will. So this is and they have big problem consequences, serious consequences. Either they're injured or even killed by these chemical reactions. So be very careful. And if you are interested in the details, and you can check the literature to see and how people found this F and found this FR, and how what problems they have caused to people. And then we talk about this ionic the bond. Ionic bond, this is it happens between a metal and a non-metal, and this if a metal and non-metal, and they have chemical reaction, and in this chemical reaction, the metallic element will donate electrons, and the non-metal element will accept electrons. So then this metal and non-metal, and they both of them can reach the stable state. So this kind of bond we call ionic bond. Ionic bond is very strong. So for example, the similar electron negativities. For example, this is MgO and MgO. Mg, we have this kind of electronic configurations. Oxygen, we have this electronic configuration, and we can see that. So this is 1s, 2s, 3s, and they can just give up this 3s2, right? And this is 3s2, and they become this is a neon this is electron configuration. You only have 1s2, 2s2, 2p6. So then have this becomes Mg, and this is ion, positive ion, right? Positive ion here. So O2, O oxygen, and this guy obtains 2 electrons from Mg, and so they reached 1s, 2s, 2p6. You can see 2s2, 2p6, 2 plus 6 equals 8. That means this guy reaches steady state, and so this guy reaches steady state. That means MgO, both of MgO, so this we call the third material, reaches the stable state. And this, you need to know that MgO has different mechanical properties and chemical properties from the metal Mg and the non-metal oxygen. And be very, very careful. MgO is treated as the third different material here. You can see, and for both Mg and O, and they reach, and they have reached the neon unstable state. We continue ionic bonding. So this ionic bonding occurs between the positive and negative ions, and ionic bonding requires electron. This is a transfer from metal to the non-metal. A large difference in electromagnetic require. Large difference. The larger, the easier. The larger the electronegativity, the larger difference in the electronegativity, the easier it is to have this is the chemical reaction and reach to have this ionic the bonding. For example, this is sodium chloride. Right? This is sodium chloride. Sodium Na is metal. It is unstable, and chloride is non-metal, is also unstable. But when these two guys meet each other, and they will sodium will become stable after he give up the electrons. And this is electron. Excuse me. And so this becomes cation. So these are positive ions. And so this is a chloride. This chloride here, Cl, and after this guy gives obtain electron from this is sodium, and so this guy also reaches the stable state, and so this guy becomes a negative ion. We call anion. So this is the we have this is a Coulombic the attraction to each other. And then we continue ionic bonding energy. So minimum energy, most stable. Energy balance of attractive and repulsive terms. So here, look at this picture. And so here, so this one is, excuse me, the potential energy E. This is below the zero with attraction, and above zero we have repulsion. Right? We have repulsion, and here is interatomic separation R, the distance between these two atoms here. And we know that atomic potential R, when this is equilibrium state here, an equilibrium state, and we have this equilibrium state. If this above this equilibrium state, and we have this is attraction. This is equilibrium state. And above this is equilibrium state, we have attraction. And if the distance is below the equilibrium state, equilibrium distance, and we have repulsion. And there is at one state the repulsion energy and this attractive energy, and they are equal. How say? So we have reached the energy balance of attractive and repulsive the terms here, En here, and En equals, this is the balance, and Ea plus this Er here, right? So Ea is attractive and Er is repulsive. Repulsive means that when these two atoms comes too close, they will have the repulsive force, and as a result, they have repulsive energy. And however, on the contrary, if these two atoms becomes have more distance, and this is the distance becomes larger, and they have attractive force and attractive energy. And so we come back to this is a periodic the table again. And so this is a predominant bonding in ceramics, ionic bonding. So this side, okay, so this side, and they give up, they have tendency to give up electrons. So these elements, they have the tendency to acquire electrons in order to achieve the stable state. So for here, sodium chloride and NaCl. So here is 0.9, here is 3.0, and so we have MgO, calcium fluoride, and so this is calcium fluoride, and this is CaCl. This is ionic bonding. We talk about ionic bonding. This ionic bonding usually very strong, and then we talk about covalent bonding. You can see covalent bonding, and they are different from ionic bonding in terms of the strength, magnitude of this is the strength, and similar electronegativity. And so if these atoms they have similar electronegativity, they have the tendency to form covalent bonding, which means that because they have similar electronegativity, so these atoms, different atoms, they have the tendency to share electrons, because they have similar electronegativities. They have almost have the same same the strength to obtain electrons or to give up electrons. So if they cannot defeat each other, and so they can share some electrons in order to make sure each of them can achieve the stable state. And for this is a bond determined by valence. S and P orbitals dominant bonding. For example, so this is a CH4, and this is CH4 is a carbon, H is a hydrogen, and so this is a, you can see a carbon has 4 valence, and need to achieve stable state, it needs 4 more the electrons. The hydrogen has 1 valence, right? And it needs 1 electron, additional electron to achieve stable state. And so they can see electronegativity and are comparable for C and carbon and hydrogen. And then, so you can see physically, chemically, so this is a C1C, and 1C, because 1C, 1 carbon, it needs 4 additional electrons from outside to achieve steady state. And so this is, if we have 4 hydrogen atoms, each of these hydrogen atoms can share 1 electron with this carbon to make sure that each of these hydrogen atoms achieve can achieve stable state, and also the carbon can achieve stable state as well. So these are shared electrons from hydrogen atoms. So this is a red dot. So these are dark dot shared electrons from the carbon atoms. Of this chemical reaction, both carbon and hydrogen atoms, and these are 5 atoms, and they reach the stable state. And then we talk about primary bonding, and for this is for the metallic, the bond, and delocalized as electron this cloud. And ionic covalent mixed bonding, and so this one can be calculated using this equation. This is a percentage of ionic character, and so here is 1 minus E, so the power is XA and XB. XA and XB are Pauling electronegativities of these 2 elements, right? So we can use this equation to calculate the percentage of ionic character. Here give one example, and for this Mg, this is Pauling electronegativity equals 1.2, XO equals 3.5. If we use this equation here, and we can calculate this is a percentage of the ionic character equals 73.4%. And then we talk about secondary bonding. A secondary bonding arises from interaction between the dipoles. So this is the dipole. So here is a give example. Here is a fluctuating dipole, right? This is asymmetric electron clouds. This asymmetric, this is electron clouds here. This is the one atom, they have positive on this end, negative on this end. So same thing, positive here, negative here, one atom. So these 2 guys, and the negative, positive, and they can form a bond, which is called a secondary bonding, and which is much weaker than the primary bonding. So this is fluctuating dipoles here. So here is, for example, liquid and hydrogen. For liquid hydrogen here, so here is H, these are protons, so it's negative, protons positive here, negative here. So here, positive here, positive here, negative here. So these we can form a secondary bond in this area. So these fluctuating dipoles. So these permanent dipoles are this molecule induced. So for example, generic case, and for here, this is positive, and usually is metal. This negative, usually non-metal. And so here, so this is a molecule. So this is another molecule. And for this negative and this positive, and they can form the secondary bonding. And I also say the secondary bonding, as the name suggests, the secondary bonding here usually means that the strength is very, very weak, the weak bonding. This liquid, and this is hydrogen chloride. So here is HCl, and this is HCl. For example, these are polymers. These polymers, this is one chain, and this another chain, and this chain to chain, and we have secondary bonding as well. So summary, the bonding, the type, bond energy, and comments. The ionic, the bond energy is very large, it's very strong, and this non-directional, for example, ceramics. The covalent, and the atoms share the covalence electrons. So variable, it determines the difference between the electronegativity of these different atoms. So large diamond and small bismuth. So they are directional, for example, the semiconductors, ceramics, polymer chains. Metallic, variable, also variable, right? It depends on what kind of materials. Large, for example, tungsten. Small, mercury. Mercury is a liquid metal, right? We know that a liquid metal, and usually they are non-directional. The secondary smallest, and directional interchain for polymers, the intermolecular. The properties are from bonding, the Tm. Right? Tm is the melting temperature. The bond length, so this is the bond length R. So this is the two atoms, this is bond length R. So melting temperature, and so this is bond energy, and this EO here, this energy. This is the equilibrium state. So this is bonding energy. And distance goes too long, R is too big, and it goes very, it reduces very substantially. So here, so this is, if this R is very small, we have repulsive this force and repulsive energy. So here is melting temperature. Okay, so this melting temperature. This Tm is larger if EO is larger. If the EO is larger, you can see the temperature property is determined by this is atomic structure, and E0 is determined by the atomic structure. So this is energy, the larger Tm, so they have larger Tm, this is a smaller Tm, because here at this state of equilibrium, so this E0 for this blue curve is lower than the E0 at for this is the dark the curve. You can see this guy has larger melting temperature. The properties from bonding, this is from this is thermal expansion, and this is CTE, a coefficient of thermal expansion. So this is the length L0, just when we heat it, and so this guy's the length changes, the change is delta L, and so we have coefficient of thermal expansion delta L divided by the original L equals alpha T2 minus T1. T alpha is called coefficient of thermal expansion. You can see here, okay? So, and also this property is determined by this atomic structure. You can see we have two curves here. For this curve, they have larger alpha, and so this is curve, they have small alpha. What it means that? It means that so this one is much easier to change the length. Why? We can see that, right? So because this guy has lower this E0. So this guy have higher E0. Higher E0 means that you need more energy and to expand. But lower E0 means that it needs small energy and to expand. So as a result, so this alpha prime for this one, it is higher than this one. So summary, the primary bonds, the ceramic, metal, different materials, polymer. For ceramics, we have large bond energy, and it contains ionic and covalent bonding, ionic covalent bonding. And for metals, this metallic bonding have variable bond energy, moderate melting temperature, moderate Young's modulus, and moderate coefficient of thermal expansion alpha. And for this is a ceramic, large temperature, melting temperature, large Young's modulus, and small this alpha, because its energy is very high. And for polymer, also polymers contain both covalent and secondary. And for this guy, and we have directional properties. You can see where this is understandable. Directional means that, for example, along this chain, it is strong, and this is perpendicular to this chain. Here, interchain, we have very, very small secondary bonding. So for this kind of material, we have small Tm, small e, and this large alpha.